My name's Clint, and this is Niraj. I'm on the geoprocessing team at Esri, and he's on spatial analyst. We both work very closely with ArcPy, and we're here today to talk about multiprocessing with both vector and rasters using ArcPy. So just to quickly go over what we'll actually cover today, it starts at a little bit of a higher level, talking about what multiprocessing is and what it's not. Then just a general demo of the pure Python multiprocessing modules, multiprocessing itself, subprocess, and then a related module that's in Python 3.5 and 3.6 called async IO. Once that's been covered, we'll move into actual code samples for multiprocessing in GIS and discuss a little bit of the conceptual side of that. Starting first with the raster concepts and some code samples of multiprocessing with rasters, and then into the vector concepts. We'll round it out with the best practices and some resources that you might find useful. So, first of all, as I mentioned, we'll talk just about pure Python. This doesn't involve ArcPy just yet, but the foundational concepts are very important to understand in a thorough way. There seems to be sometimes a little bit of confusion, especially when just getting started with these concepts, between what multiprocessing and concurrency are. So we'll start with discussing multiprocessing itself. I find a good analogy for this, at least in my mind, is to think about road systems and highway systems. And it's an interesting way to kind of segue from GIS into a talk on multiprocessing. I'm originally from Canada. We have a single highway that goes all the way across the country called the Trans-Canada Highway. And if there's ever a blizzard or an avalanche, the highway literally freezes like a computer program can. The trucks that ship food across the country can be kind of thought of as the data in your programs. And if they get caught up, they're all stuck until that freeze gets cleared up and they can start moving again. Sometimes that can take days, and that's really akin to when you just sit there on a computer and nothing's happening in your program. On older computers, like when I started programming, you typically just had a single CPU, as opposed to modern computers where you can have 4, 8, 16, or even more on servers. So that single core is exactly like that highway. If something freezes on it, it just hangs and hangs, and nothing really works until that program catches up with itself and keeps going. However, on more modern processors, you could have more than one process going at a time. So if a single one should actually start hanging, you still have the other ones to rely on. This is more akin to the highway system here in Southern California, which I kind of think is one of the wonders of the modern world, quite frankly. It's really encouraged me to think very differently about how computer programs themselves run. There's multiple lanes, in many cases 4 or 5 lanes per highway. That allows for fault tolerance. So if there is an accident or a disaster in some of those lanes, they can be shut down and dealt with, while the others allow traffic to continue to flow. Additionally, there's more than one highway. So if one is completely inaccessible for some reason, for example, the forest fires that have been happening recently, there's still this entire network of other highways that you can proceed on. When thinking about a program, in a modern context, you can effectively build multiple highways, so to speak, in multiple processes, and if one of them fails, the rest will keep going. That one can be dealt with programmatically, kind of akin to a tow truck taking a broken down truck off the road, and keep on moving. Now, within each one of those lanes, there's also the kind of concept that cars can pass one another. To me, this is more what we're talking about when we're saying concurrency. That's essentially allowing more than one operation to happen in a single thread. or a single process, I should say. This can be thought of also, for another analogy, as threads, and we'll see why in a second. And it's really kind of like you're twisting a whole bunch of things together into a single strand. So when you're looking at designing a program, there's many things that you'd consider. The cost of the actual development time and the underlying hardware that may be necessary to run it, how many people might be using that program at any given time, or how much data might be coming through that program at any given time. And also the complexity of the interoperability between that program, the underlying operating system, and any other consumers. For example, another service that might take the data from that program and do something else with it, or the hard disk that you're actually writing the results to. Now, as I've kind of said, multiprocessing is actually not as complex as some people may think it actually is. In and of itself, it's really just running the same process side by side. So some terminology to kind of wrap your mind around that concept is if you're just having a single program that's just running a single thread or a single process, it's typically referred to as a serial program. It'll run one instruction at a time from start to finish, and if the whole thing crashes, you have to start over again or deal with that problem, and it can take quite a while. Excuse me. Concurrent programs, on the other hand, are a more complex serial program that multiple instructions will run one at a time within the process, and effectively one of those may sleep while another one runs. If you're familiar with Python, you might have heard of something called the global interpreter lock. This is a concurrency problem in Python that's got some bad rap. There's been lots of work to get around it since Python itself has been lots of work has gone into Python, I should say, so it's a much more mature language than it was, especially when ArcPy was developed. ArcPy itself actually was developed before Python even had Booleans. It just used zeros and ones to represent false and true. So lots has changed, and therefore there's some considerations that you have to take into effect when using ArcPy in this fashion. That global interpreter lock that I just mentioned, it can kind of almost be thought of if you're driving in a foreign city. For example, if all of the street signs are in C and you have an interpreter that speaks C and you happen to be a snake that speaks Python, that interpreter is a parcel tongue for any Harry Potter fans that can change the C code into Python. But if that interpreter needs to sleep for a moment in time, you're actually kind of stuck there. So the way that we would look at getting around this is effectively using multiprocessing. To take that further, you can also look at decentralized programs that run on multiple computers on a network or multiple services on a server, as servers usually have much more hardware than a standard desktop. This is usually controlled by some kind of central hub that would then aggregate all of the information coming from these multiple computers. That can usually be something like a dashboard on your screen, or even ArcGIS that's taking many data sources and then putting it up into one single unit of information that can be digested. Taking that even one step further, there's distributed programs as well. We won't be talking much about that, but if you are interested in taking multiprocessing and those concepts to the next level, I would certainly recommend looking into distributed programming. And especially, there's a Python package that I really like to advocate known as Dask, D-A-S-K. That's put out by one of our partners, previously Continuum Analytics, now known as Anaconda. And that really allows you to create a program that will work either in parallel on a single computer or across a distributed network or high-performance cluster. Some of the concepts that would be in an ideal world if you were starting on a greenfield project and wanting to look into multiprocessing, in the context of Python specifically, would leverage some of the more modern Python paradigms. ArcPy has been updated to leverage many of these paradigms, and we'll get into that in just a moment. But to kind of cover some of those ideals, first of all, loops themselves can be kind of thought of as that form of congestion. So instead of having a function looping over and over again, it's actually usually better in a multiprocessing world to use parallelized iteration and iterators or generator statements. If you're dealing with a very, very large data set that may take more than your computer RAM has available, a generator is actually the exact way to get around that problem, as it yields a single unit of data. And that can almost be thought of as some of the on-ramps around here have little red and green stoplights. So as you're pulling onto the highway, it'll iterate or generate a single car out onto that highway and make it more manageable so that it doesn't all get congested at once. If you can combine both multiprocessing and concurrency, then you're basically making the most out of each one of those lanes. The lanes are full of cars that have a driver and a passenger that can alternate back and forth as one of them needs to sleep. And should one of those lanes have problems, the fault tolerance allows you to essentially try again, use a callback to tell your hub program that something went wrong and to send more resources to it perhaps, or anything along those lines that will make the program flow in a way that you can anticipate and effectively get all of the data where it needs to be by the time it needs to be there. You can throttle your input or use a mapping function in many cases to effectively give each one of those pieces of data the same function, and as I mentioned before, anticipate what is actually going to happen in the program. Typically, you're either going to want to have the program put all of those units of data or cars back to their home. So to me, that is either putting it into a memory location or putting it into a hard disk, or pass it off into another county or state's network, which is akin to passing it into another program. While you're doing this, it's also important to remember that you can aggregate data at many steps within a multiprocessing blueprint, effectively. So if this can kind of be looked at as when you're moving from a single lane road into the larger roads and then back down into the single lane roads. As the data is kind of combined into a larger unit, stuff is done with it, and then it's put to where it needs to be based off the address that results or the value that results into a conditional statement. The actual modules that Python itself provides without having to download any packages or install anything but Python itself are threading, which in and of itself is actually a very, very specific thing. So unless you know you need to use threading, it's very unlikely that you'll actually need to do so. If you're creating a framework for someone else's consumption, this is probably when you'll need to look at that. But if you're creating a script, then it's very likely that that's too low level for what you're wanting to do. So in that point in time, it would be much more fortuitous to use multiprocessing or subprocesses, and I'll talk a little bit about the difference in just a moment here. But the kind of general idea is that multiprocessing creates multiple instances of Python doing the same thing. This is not subject to the global interpreter lock problem like concurrency is, because you actually have several interpreters in that case. So it's not just one that you're overloading with too much information, but multiple clones of that same instance. And then the underlying operating system at that point is what's actually implemented threading that allows it to utilize the hardware in the best way possible. Now, A different concept, but similar in nature, is subprocessing, which typically is used to launch non-Python processes. So say, for example, somewhere in your script you needed, if you were, say, writing Git, and then needed Vim to pop up to write the commit message. It's launching Vim as a subprocess, waiting for it to return something, in this case the commit message, and then continuing on with the initial process. Subprocesses could be a serial program like Vim, or themselves could actually launch multiple processes in parallel. I also mentioned the notion of a callback. That's effectively a function that allows that subprocess to communicate back to the original process. And we won't be covering that very much in this talk, but it is a very useful concept to know if you're going to write complex programs. Prior to Python 3.5 and 3.6, there was a module known as Twisted, and it still exists, but it's kind of been replaced by async I/O. Twisted itself was a framework that effectively implemented threading for you and made concurrency very easy. It hasn't gone away because there's a lot of extra work that's been done there to facilitate things like video or audio or even user interface interaction. So if you're looking to write a Python program that has an interface element or some multimedia in it, then Twisted is a good way to go. However, if you're wanting to implement concurrency on your own, in Python 3.5 and 3.6, async I/O uses a very similar pattern to other languages like C#, for example, using an asynchronous and await pattern, which I'll talk about in just a moment here. So I've just made a couple little animations here to illustrate these concepts in a more meaningful visual manner. The code itself is just general code to kind of get this stuff working in the command line, so I won't go over it too much, but I will just point out it's using a nifty little package called TQDM, which is really neat and just makes these progress bars on the command line super easy. Effectively, as you can see here, there's 4 processes that have been called by the multiprocessing module. Near the bottom, there's the MP handler function, which creates a pool of 4 processes and then maps the multiprocessing worker function to each unit of data that is in the data variable, that's the enumeration that's defined near the top. Each one of these has a different delay implemented in it for each 5% unit. So you can see C itself is the fastest one, A is second fastest, B, and then D. And those can kind of be thought as people driving at different speeds on the highway. They'll all eventually get to the end, and at that point in time, you can take that data and re-aggregate it into a unit of information. Now, subprocess, as I said, is like calling an additional process. So to me, that's kind of like you drive along, hit a red light, and then another dimension of traffic moves through. In this case, I'm listing a whole bunch of Python packages that are in this environment, and then finishing up that process. Lastly, I'll talk about concurrency, just to illustrate what's going on here. Excuse me, there's several different routines that are being run that are just making a simple HTTP call that has a randomized delay to it. And the important point that I want to illustrate is in those, or sorry, I should say 5 different indexes that are up there. The delays are actually something that can be anticipated. So you'll see that the first one has a 5-second delay, the fourth one has a 5-second delay, 0 and 4 have a 5-second delay, 1 has a 6-second delay, and 2 and 3 have an 8-second delay. And then the resulting HTTP calls actually come out in that exact same fashion. So if you are needing to marshal these sub-processes or concurrency, you can definitely anticipate that. So now I'll pass it over to Niraj for a little bit, and we'll talk about the concepts of multiprocessing and concurrency in GIS.
All right. Thank you, Clinton. Hi, everyone. My name is Niraj. I'm from the Spatial Analyst team at Esri. So Clinton walked us through some of the fundamentals of concurrency, threading, multiprocessing, and then the modules available on Python and their capabilities. So today what I'll be talking about is how some of these concepts are relevant to GIS and how they can be applied to solve your geoprocessing tasks. I will focus on raster analysis using multiprocessing, and we'll also look at some demo with some code. Following which, I'll return the mic to Clinton, and he will discuss vector analysis using multiprocessing. Right? So let's get started. GIS is the language of geography, profound words from Jack from UC 2004. Our lead developer, Bill Moreland, also quoted, Python is the language of GIS. So we do understand that GIS is inherently more complex than Python itself, as we are dealing with spatial data, projections, etc. So what's the problem that we're trying to solve today? The overall broad problem we're trying to solve is to improve performance and scalability of complex geoprocessing tasks, be it raster or vector analysis. So let's talk about how to work with rasters in multiprocessing. I'd like to think of two candidate operations for parallelization when it comes to raster analysis. The first class is to parallelize independent tasks within a geoprocessing workflow. So this is a workflow that you may, say, write on Model Builder, or it may be a series of tools that you run. It could be a Python script where you have chained together some GP tools. So the common approach to do this would be in a serial fashion where you would use one worker process to execute these tools. So what I have here in this graphic is a suitability model workflow where I'm running 4 different analysis tools, and all tools are executed one after the other. So you start with the slope tool, the aspect tool, reclassify, and finally the weighted sum tool is executed. So looking at this workflow, we can quickly identify that there are some independent units of processing to this workflow. So the slope tool, the aspect tool, and reclassify tool, their execution is an independent task. They don't have any interdependencies. Whereas the weighted sum tool in this workflow is a dependent task. It has a dependency on the outputs from these other 3 tools to complete executing before it can begin its execution. So how may we redesign such a workflow to attack it in a parallel fashion? You may do something like this, where now you're leveraging multiple worker processes in modern infrastructure, and you are executing those independent tasks simultaneously. And whereas the weighted sum task, which is a dependent one, still has to wait for those dependencies to come through. So you can think about how, if you have a more complex workflow with a lot more tools, how you could identify these independent units and execute them simultaneously instead of just having one worker process go through the entire chain, and that becomes slower. Right? So the second class of problem that I'd like to think of when it comes to parallelization is processing a really large raster. So you may have a raster with billions of data points for the entire United States or the entire world. And today, with increasing resolution, these data sizes have grown considerably. So today I will limit my discussion to local, focal, and zonal raster operations. So let's digress for a moment to understand what are these different class of raster operations. So the first class would be local operations, where this is a per cell operation where the resulting value at an output cell or location depends on the value of inputs at that location. Whereas a focal operation or a neighborhood operation has the output result at a location depending on the input value at that location and a neighborhood surrounding that input. Zonal operations are similar to focal operations in that this neighborhood is now a larger area that could represent a cartographic zone, such as a watershed or a land use type. So if you're doing zonal statistics or zonal histogram, those are all zonal tools. For the focal tools, the examples would be, say, the slope tool or the aspect tool. And then with local tools, we have tools such as sine or any math function where you're simply calculating a function of a value at a cell. And then finally, we have global operations, which we won't really discuss in the context of multiprocessing. So these global operations are where the output value at a cell could potentially depend on the value of all the cells in the input raster. So it's a per raster operation. Okay. So going back to our previous example of processing a large data set parallelly, what is the standard approach in this scenario? You would simply use your GP tool, run the entire raster through it, and you will get your output. But depending on the size of your data and the frequency at which you may be running these tasks, this process can be slow and tedious. So the method to parallelize this is through data decomposition, divide and conquer, where we can decompose the input domain into partitions and leverage multiple worker processes to simultaneously work on these individual bits of our entire raster. So how do we do this programmatically? Let's look at a demo for that second use case of processing a large data set. So what I have here is a workspace that I have set up for this demo. And I have a folder with the first directory called Fishnets. Here I would be creating a feature that represents how I'd like to partition the entire processing extent and what are the extents of these individual partitions. I would like to represent that using a feature data set that I will create within this directory, my local raster workspace where I will write the output of these individual processed extents. And then finally, I will mosaic them all together to get my final output in this mosaic file geodatabase. And finally, I have my input raster itself. Then I also have my program to do all this work, which I'm calling parallel local. So this is a Python file. So let's look at this program to see what's going on. So I have the entire program here, and I have collapsed some sections towards the end. So let's go through it from start and see what's going on. In the first section, I'm just importing some necessary modules. I'm grabbing my ArcPy module that I need for my geoprocessing. I'm obviously getting some functions from the multiprocessing module, such as the pool function and then CPU count to give me an idea of how many processes am I working with. And then I'm setting some ArcPy environments. I'm going to use my Scratch workspace for intermediate data sets as my in-memory workspace. Instead of writing these temporary data sets to disk, I'm going to write them to memory to make the entire process faster. I'm going to use a logger to report how long these processes take. And then we have a couple of functions that we will get to shortly. And then we have the main function where the main code is executed. So let's start with the main function and look at that. And this is how the code would progress. So I'm starting my clock here to keep track of how long this entire process takes. The first thing I do is I'm calling my create fishnet function, which would create those fishnet features I discussed. These are the features that represent how I'm partitioning my entire processing extent. So once I run that, my fishnet features are created. And then I am storing the extents of these fishnets into a dictionary in the second block of code here. Once I've created this dictionary of extents for these individual partitions, I am creating a processing pool using the pool function from the multiprocessing module. And here I'm creating a pool equal to the number of CPUs I have. And then to that pool, I'm mapping my execute task function. So the execute task function, we'll look at that shortly. This function is where the actual geoprocessing tool would be run. And then I'm passing to that function some arguments, which is my dictionary items. And these items represent the partition extents for each of those spatial partitions. So then my process pool would have, say, 8 processes working simultaneously on each of these individual extents. And the reason why at this stage I'm not directly passing, say, a raster or the fishnet feature itself is because these geoprocessing objects, they are not pickable. And what this means is that you may not pass these objects from a master process to a child process across the wire. And in order to work with pickable types, I'm using a dictionary. So once that is done, these individual processes are going to go do the processing. And then when I call join, it's going to wait. It's going to block this main code until all the other pools in the processes in the pool have completed executing. And once that is done, I'm going to add my outputs to a mosaic data set. And that way I'm combining all these individual chunks back into the complete raster that represents the extent of my input. And then I'm keeping track of time to know how long this entire process takes. So now let's go look at the create fishnet function. We had collapsed that earlier, so now we'll go see what's going on there. And within this block of code, what I'm mainly doing is I'm executing in the second to last line is the create fishnet tool, which is going to create these fishnet features. And here I can specify, if you see the number of rows and columns, I've specified that as 4 and 4. So I have 4 times 4, which is 16. So I have 16 partitions for my entire input processing extent. This is the execute task function where the actual GP tool is run. And it takes an argument, which is the extent on which it is expected to process, right? So within here, I'm setting some environments. I need to set my snap raster environment to make sure my rasters aren't moved about or resampled. I'm also going to set my cell size for that same reason. And then I'm going to set the extent as this partitioned extent on which I'd like this process to focus its work on. Okay. And then I'm actually running the raster analysis tool, which in this example, I'm running the square root math tool. And then I'm writing that output. So this entire execute task function, to reiterate, would be run by all these processes simultaneously on different pieces of data in different extents. If you could hold your questions till the last moment, that would be great. Thank you. All right, so if I were to run this code, it would spawn some worker processes, And then here you can see the different process IDs. There are about 8 processes here. And since I've created 16 chunks, I have more chunks than processes. So initially you would have these 8 processes get spawned up. And as soon as any one of them finishes, it would go grab the next extent that it has to work on. So there is no waiting around for all the other processes to complete. And then it would write all these on the right. It would write all these output chunks, which I would finally mosaic together to get my final output. So this is a lot of work. Why would you go about doing all this? You could have simply run the GP tool and be done with it. Well, the whole purpose is to make it faster, to improve performance, where it could be beneficial to you. And what I plotted here is how performance improves as we go through this process. And we can see that going from 1 to 4, the gains are more obvious, and they do start flattening out after that, and you're not getting too many performance gains. These could be due to a variety of overheads. So if you're trying to implement such a method for your process, it would be sort of a trial and error experiment where you would have to determine the optimal number of processes that I would need to use so that I'm not using too many and choking up my system resources, that I'm using the right number. All right, going back to Clinton.
Thank you. So vectors themselves are a little bit easier to conceptually work with, at least compared to raster, because there is not that consideration of the different types, for example, focal or local or global. There's discrete units of data that you are passing off in a scalar fashion to different functions. So this is where, for example, the yield function or the concept of generators in Python may come into play. Now, we saw on Neeraj's slides previously that there was kind of that step where the multiple processes went back into the hub process and got put into the mosaic data set. That's the process of aggregation that we had previously discussed. And effectively, that can be done not only once in a program if you're wanting to make it very complex. You can have multiple times that that data gets aggregated and then perhaps even expanded back out again, and so on and so forth. Now, you can have in Python, there's multiple collection types. So for example, there is the dictionary that was previously referenced. Of course, there's a list, which is common across many programming languages. There's also a set, which is a very useful way to reduce the amount of results that you get if you're looking just for unique values, for example. And these are all advantageous, as was previously mentioned, because they're picklable. So when you're working generally with vectors, one of the things that we recommend doing is trying to use cursors to effectively pull the pieces of data into a pure Python data set and then pass that off to multiple processes. The underlying part of pickling itself requires the data to be hashable. So effectively, that needs to be immutable. So the reason that geoprocessing objects like geometry can't be pickled at this point in time, which is something we're working on, is that the underlying plane upon which they exist is theoretically infinite. You can go down to any level of precision. So to actually hash that right now is a relatively difficult step. But if you can define the precision that your program is working to and then take those values from an ArcPy object and then pass it into something that multiprocessing can use natively, it will allow things to just flow a lot more easily. Now, another thing that I'd mentioned before is that you're either going to try and return a result set in which everything has been aggregated into more consumable units of data, or you can have those come out as discrete results as well. Something that you could look at perhaps as a example of an aggregated result is, if you have a whole bunch of points that you just simply want to buffer, and then take that buffer from each point and then union it together, you can do that. Or have a collection of points that come and just simply aggregate those into a line or into the border of a polygon. Now, for discrete results, you may want to do something, for example, with tweets off Twitter. Each one of those data points is discrete, and you're not going to buffer it, you're not going to do anything with it, but you might, say, perform semantic analysis or geocoding on it. Each one of those data points can then be sent out and don't really influence one another. So at that point in time, you can do anything that you want with those, and effectively that's one of the better ways to pass data when you're using a web service, for example, because with tweets, you may just continuously harvest them for a week or a year, who knows how long. So in that case, just because you're dealing with one at a time as opposed to a giant collection of them, you can be sure that your memory footprint should generally stay the same, and you won't encounter errors for your system resources. Now, this is a similar type of demo in that we'll just talk through the code and the concepts behind it. So in many ways, what we're looking at doing here is a similar process to the fishnetting on a raster, when you're taking a sizable set of data and then breaking it down into batches or ranges, whichever terminology you prefer to use, and passing each one of those off to a pool. In this case, as opposed to using a raster tool in the spatial analyst package, we'll use a generate near table tool that's in the geoprocessing tools, and we'll look at that in just a moment here. Another interesting thing to note is that NumPy arrays are natively created to work with this type of data. So if you are looking to have a very performant approach to multiprocessing, you may want to get familiar with the NumPy package. We do have several functions included with ArcPy that natively transfer either rasters or vectors into NumPy arrays, and those are in the DA or data access module that comes with ArcPy. And again, it's just worth mentioning that you always want to be careful to close and join the pools that you're doing multiprocessing with, just to ensure that there's proper cleanup, that all of the memory addresses are freed up, and that you don't encounter errors that you may otherwise be, that may otherwise cause circumstances in the program that may not even cause it to crash, but just have weird results. The generate near table function that I previously mentioned there, in this case would take points and effectively use the analysis tool, generate near table, to create all of that. So I won't spend too much time going over this code here, but effectively you can see that we're using several tools right here that can, from the geoprocessing world, effectively, that have multiple ways of interacting with the data that you'll use. So you'll see about midway down the screen there that I'm providing a SQL statement, and that's an excellent way to filter your data right at the source. So as opposed to having all of the data flow through the program and then discard some of it, this is only getting the data that you want. There's many different ways to ensure this type of thing happens with ArcPy, but I find SQL statements are very familiar to many programmers and a very good way to start looking into this. And then if you can also integrate that concept into generator statements, then it becomes very, very powerful. You'll see again, just I'm using the table to NumPy array with a typo in it. I apologize for that. And using the delete management tool to clean things up at the very end as well. So on this slide, it's just another type of approach, but we're effectively using multiple SQL statements and cursors, which are a very, very important thing to note when talking about multiprocessing. I mentioned them briefly before, but effectively the cursors that are provided in the data access module are a more modern addition to ArcPy than its original design. So they do leverage a lot of this newer paradigm of Python. So if you are wanting to use generator statements, if you are wanting to use comprehensions in which you can have a single line which populates an entire collection with data, you'd want to look into those data access cursors as opposed to just the ArcPy dot search cursor or insert cursor of the same name, just because those have existed for many years prior to that and don't have quite as much robustness built into them. In all of these examples, you'll see that there's some kind of concept of breaking a larger data set down. So near the bottom here, I'm breaking these points down into 2,000 data point collections as opposed to trying to pass the whole thing through. And again, that's more so to just pass these chunks of data into the programs as opposed to trying to get it all processed at once. So just to touch on a couple of the points that may not have been popped out at you, the in-memory workspace is a very important thing to consider using when multiprocessing. You want to try and use as much of the faster hardware in your computer in this case as possible. So there's generally a hierarchy that CPU and CPU caches are the fastest thing, memory's a little bit slower, but quite a bit faster than writing to disk. So try not to write to disk until the very end or read from disk at the very beginning, because that can introduce delays into your program that might reduce the advantages that you would see, for example, in the graph that Neeraj had provided. Additionally, when you're writing and trying to process multiple batches or slices at once, try not to write into a file geodatabase, or if you're doing that, don't write into the same file geodatabase. I'm sure we've all experienced locking problems before, so it can be a very, very maddening task to try and write everything into the same one. As opposed to doing that, just create multiple file geodatabases and write into several of them at the same, or in parallel, and then aggregate at the end. And then, and lastly, if you are performing these in ArcMap or in the 10x series of software, you will definitely want to look into 64-bit processing. It will just free up the amount of RAM that you're available to use. And in most cases, there's a few very far edge cases in which 32-bit is a limitation these days, but most computers allow 64-bit processing. So looking ahead at some of the ways to actually extend these concepts, I had previously mentioned Dask. I find that is a very useful library. And even if you want to go and look at the underlying code, it really elucidates how a lot of these concepts work. If you're wanting to supplement multiprocessing with asynchrony, look into using async IO, as it's the most fully developed Python module at this point in time, or Twisted, as I previously mentioned, if you have, again, multimedia or user interface considerations. And also, if you are in a situation where you have access to ArcGIS Enterprise and Desktop, it's certainly worth considering that interoperability with services on a server and essentially consuming them through a REST endpoint is very complementary to multiprocessing because you are not trying to read off a single hard drive. So it essentially removes the bottleneck that may be present when trying to work all on local hardware. It's also actually a good way that you can chain services together in that you can consume from one REST endpoint, do some processing locally, and then put it up to another, and then that may have some kind of reactive consequences further down the line that will again start to process things. And that, to me, is how most dashboard applications should be viewed, in that they can, essentially, based on what the user is requesting, there's a reactive component to what you're actually doing in the multiple processes. I'm also seeing people take pictures. Just for the reference, this talk is up on YouTube, and we'll put the newer slides up on SlideShare as well. But here are some resources, which you can't click on right now, but you can if you get it later. There's the sample scripts that Niraj wrote, available in the top link, as well as a blog post. Actually, we didn't update this slide, but there's an older blog post there. Oh, you did update this slide, my bad. About vector processing, which wasn't written by myself, it was written by a previous product engineer on the geoprocessing team. And Niraj has just authored a brand new blog post with these concepts at the third link there. It's probably still on the front page of the Esri blog, so definitely check it out if you want to follow up on this session. And also, the Python 3.5 or 3.6 multiprocessing API is kind of the place where you'd want to start learning about the nitty-gritty part of it. We did a high-level overview, but there's a lot more functionality and a lot more description, if you want to actually really understand the computer science behind it, that the Python documents do a fascinating job of describing. So we've left about 8 to 10 minutes here for some questions, and we'll also, at least I'll be at the Python ArcPy island for the rest of the day as well. So thanks for coming. And if you have any questions, we'll just bring the mic down to you so it gets on the recording as well.
Thank you, everyone.
Hello. You mentioned writing to multiple file geodatabases. What if you're using SDE?
Right. So if you're using SDE, that is, sorry, I'll just hold it. Certainly, like I was saying with the REST endpoints, a similar concept to using a service, in that it's typically going to be on a different physical device, and therefore won't have all of the bottlenecking that you'd see on a local machine. So it really does depend, of course, at that point on the speed of the connection between the machines, and also if that SDE machine itself has multiple disks that can be leveraged and everything like that. Typically, a database server would be in a RAID configuration or something along those lines that would alleviate some of those concerns, but still be worth measuring depending on how quickly you're processing the individual units of data. So, for example, if you're just doing like a large amount of addition operations, you still may be able to flood the database and cause that bottleneck because it's a very, very quick CPU operation. But if it's something more like buffer or some of the raster functions, for example, then that may introduce enough delay per unit of data that you can still kind of see it flow through in a performant way. So there is some trial and error to that, and like I say, it also depends on the system itself. So if you need a very, very high availability system that has like a service level agreement of a very low processing time, then you may need to up the hardware that you have in the back end as well. So it really depends on a lot of circumstances in that case. But generally speaking, it's a much better way to do things, and typically you can all write to the same database table if it's configured correctly.
Is it possible to use InMemory Workspace on another machine?
Yeah, well, that could certainly be a possibility. The InMemory Workspace itself is slightly limited, so that's also important to keep in mind if you're wanting to leverage things that are built into a file geodatabase. Then, for example, extracting a geometry object, when it's all said and done, then it may be better to get a performant disk and use that. However, you can basically think as the in-memory workspace as limited to being a shape file. That's not exactly what it is, but it has almost the same limitations to it. So as long as that works for what you're doing, then distributing that across multiple machines could certainly be advantageous if that hardware is available. At that point, it also does introduce some licensing questions as well. At my previous job, we had 8 ArcInfo licenses, and there was times that I'd come in at night on the weekend and run it on multiple machines because it would go a lot quicker. But then trying to run that, first thing Monday morning would get me hate email. So it really depends on the environment.
Any other questions?
Yeah, so I was curious on your example where you had the 16, you broke the raster into 16 pieces, and then you had the graph where the performance, the latency was kind of bottomed out. Mm-hmm. Can you explain why, after maybe 4 processors, you're not really getting more in performance?
So in that situation, I'm not exactly sure what the overheads were. I didn't really go into the effort of measuring it, but I'm assuming that at that stage, memory was an issue. That it's just that with so many processors trying to access the same in-memory workspace, that it wasn't giving me the performance I want, and that with better hardware, I would see that flattening out much further down the line.
Like if you had a ton of memory, it might drop farther, but then maybe the disk was trying
or if I had more than in this scenario, what I had shown was simply on a single machine with 8 cores. But if I had, say, I was doing the same thing through Arc server, and I had more than one machine and access to multiple disks. And also worth mentioning was that I was using a single disk. So that could have also been a limitation in this case.
Yes, typically that leveling out can be mitigated more so by increasing the speed or the bandwidth of the memory itself as opposed to the size of the memory. Because at that point you're kind of running into when the hierarchical nature of the bandwidth of the different hardware in the computer kind of reaches its limit. So at that point, the transfer between memory and the CPU may actually be backed up a little bit. And when it starts to really level out, then you're getting kind of a queue that's being processed at that point.
For parallelizing the focal or local algorithm on a raster, you divide the raster to separate rasters. So is it possible to run a parallel algorithm for focal or local on individual pixels and give a bunch of pixels that we go in a nested for loop, for example, through the raster in a parallel way?
Yeah, that is certainly something you can conceive. It's just that you may want to see at how many chunks is again an optimal number for my particular environment, right? So in your case, you're talking about partitioning down to the pixel level, right? So for instance, if you're doing something like converting your raster first into a NumPy array, and then in that 2-dimensional array, you have now each value is one value in that array, and then you may just use a generator or something and go through each value and process it. So in that fashion, you could do it, and maybe it's fast. But then, given the huge number of partitions and few number of CPUs that can process it simultaneously, you may not see those advantages. You may see that flattening out happening again. So it's always a balancing act.
I know some of the spatial analyst tools have a parallel processing factor environment setting. In that case, can that just be consumed and I don't have to use the multiple processing?
Yes, absolutely. So in 10.6, we introduced, in fact, a bunch of those global operations I had not discussed. And the reason was we have out-of-the-box parallelized many of these using the parallel processing factor, in which case you just set an environment variable and then we do all the heavy lifting for you and we parallelize it. So you wouldn't have to write any of this complex Python code. So at 10.6, if you're working with hydrology tools or distance tools in the spatial analyst extension, you will see that they're coming now out of the box with parallel processing. And you can expect to see that soon in the next release of Pro as well, where you also have the advantage of 64-bit.
It's 2:00, so we'll have to stop answering questions up here, but if you have any more, please feel free to come ask us down on the floor. Yeah, sure. Thank you.
Thank you.